Work, in physics, it's an indication of a change in energy, or more precisely, it's a transfer of energy from one object to another object. It can be calculated by this formula right here, work equals force times distance. But there's a special relationship. We're going to stick with the simple cases here, in which the force and the distance or the motion are in the same direction. If they're not in the same direction, you have to make some adjustments that we're not going to get into right now. But work is force times distance, and the force is in newtons, and the distance is in meters, so the work is in Newton meters, not newtons per meter, but newtons times meters. Now we have a name for this. A newton times a meter we call a joule, Joule, named after a famous scientist in the 1800s. And we're going to use a capital J to symbolize the unit joule. So to recap here, for work to be done, there must be a force applied to an object, there must be motion of the object, and the force and the motion must be in the same direction. So for example, how much work is done in lifting a 7 Newton box 3 meters? Well, if we draw the diagram, let's say we have this box and it weighs 7 newtons. Now that means gravity is pulling down with a force of 7 newtons, but your applied force to lift the box has to be 7 newtons. Actually a little bit more to get it going, but then you can keep it going with your upward force of 7 newtons to lift the box. So the work done by your force, your applied force of 7 newtons up, well, let me write it out first, force times distance. The work is going to be your 7 Newton force times the upward distance if it goes 3 meters, and the units are good, newtons and meters, that would be Newton meters. So the work done here would be 21 Newton meters, or 21 joules. So once again, just to recap over here on the side, the force is in the upward direction, the motion or the distance is in the upward direction, those are in the same direction. So that's why we can calculate the work with this simple formula right here. As opposed to problem number 2, how much work is done when we carry the same box 3 meters. And once again, it weighs 7 newtons. So gravity's trying to pull it to the floor with 7 newtons. And you're simply holding it in your hands right now. You're not lifting it any further. You have to apply a 7 Newton force to keep it stationary. But the question is, or what's going to happen here, is that the box is going to move this way 3 meters. So do you need to apply a force that way to move the box in that direction? And the answer, surprisingly, is no. You need a little bit of force to get it going, but according to Newton's first law, an object in motion stays in motion in a straight line unless acted on by an unbalanced force in that particular direction. So at low speeds, there's virtually no air resistance. When you carry a box, believe it or not, your only applied force really is the upward force of 7 newtons to keep it from falling to the ground, and just a little bit of force to get it going. But once you have it going and you're carrying it, you're not applying a sideways force. So in other words here, the work you're going to be doing is zero. There is no work that you are doing as you carry this box. Now, is zero. Now, yes, it requires effort to carry a box, but from the science standpoint, physics standpoint, no work is done. We can look at it another way. Your applied force, your force is 7 newtons up, and the motion of the box is this way, and we can see that they're in different directions. They're perpendicular. And this is the worst case scenario for getting work done from a physics standpoint. If the motion and the force applied are perpendicular, then no work is done, absolutely zero. How about this one, example number 3? Same box, okay, same box, but now it's sitting on the floor. I mean, it weighs 7 newtons, all right? So there's a 7 Newton downward force from gravity, and the floor is supporting it now. You're not holding it up, 7 newtons, all right, but you're dragging it, or you could be pushing it, either way. But you're pushing it with a force of 2 newtons to make it move to the right, so you're applying a 2 Newton force this way. Now, actually didn't say that. What it says is that friction is 2 newtons. So let's say you're trying to move it to the right. Is your actual force applied 2 newtons? Because this would now represent friction, 2 newtons of force resisting the motion. And if the box is moving, but it does say moving at a constant velocity to the right, is your force more than, less than, or equal to 2 newtons? Well, as we learned last chapter, you need a little bit more than 2 newtons to get it going, but once you have the box going, yes indeed, this 2 Newton force is what you need to keep it going, no more nor less. If you push harder than 2 newtons and friction stays at 2 newtons, the box will accelerate, but this box is not accelerating, it says it's constant velocity. If you push with a force less than friction, the box will slow down. So in other words, you're pushing with a 2 Newton force to keep the box moving at a constant velocity to the right. A little bit more to get it going, but 2 newtons to keep it going at that constant velocity. So how much work is done here? Well, once again, the formula is work equals force times distance. Now, in this case, you're not applying a 7 Newton force, you're applying a 2 Newton force. So your force that's doing work, you're doing work with an applied force of 2 newtons, and you're moving the box across the floor 3 meters. So in this case, you are doing 6 Newton meters or 6 joules of work on the box as you move the box. Okay, one more thing that I mentioned at the very top is that work indicates a change in energy. If we go back or look at the top of the page, question number 1, which I'm not looking at right now, but in question number 1 you lifted the box with a 7 Newton force in the upward direction, and you did 21 joules of work. 7 times 3 was 21 joules. That actually increases the energy of the box. You've raised it to a higher level, and on the next page of notes tomorrow or the next day, you'll see that that increases what we call the gravitational energy of the box, the gravitational potential energy. So that's an indication of an increase in energy. You're transferring energy actually from your body to the box. In part number 2, you're not giving the box any energy. Yes, it takes effort on your part, but the box is not increasing its energy level whatsoever. It's not going higher. It's not increasing its speed. So that's another indication that no work is done. In the third case, however, the box is not gaining energy either. You're doing work, but the box is not gaining energy. It theoretically should be gaining the energy put in by the amount of 6 joules in example number 3. But what's happening in problem 3, you actually are doing 6 joules of work, but friction is opposing it with the same force. And if you calculate the work done by friction here, technically it would be negative 6 joules. So you're trying to give the box 6 joules of energy, but friction is robbing the box of 6 joules of energy, so there's no net gain in energy of the box. So there's 2 things doing work in this particular problem. Your work of 6 joules and friction's work of 6 joules, because it's also 2 newtons times 3 meters opposing you. So once again, this is consistent. There would be a transfer of energy to the box if there were no friction here. And the last thing to mention again is that your applied force was this way, 2 newtons. The motion of the box was this way. That was the distance it moved. Noticing once again that the force and the distance are in the same direction. That's another indicator that work is done. And the other thing I did want to mention as well at the beginning, or well, now at the end, is that work here in physics is a transfer of energy, or an indicator of a transfer of energy. It's not like, when we talk about somebody going to work and having a job, like a teacher or a lawyer or a doctor. Obviously, the term work here is used in a different context. It's the transfer of energy, not a job.